what I want to, but even before we start, I want to sort of preface today with the fact that it is going to be a little bit different. Um, and you are going to be significantly assisted by the idea of being um, as visual as possible. So we're gonna talk through a lot of this, and I'm gonna go through, and I'm gonna try and explain it in as many different ways as I can, as best as I can. Please ask questions if you feel like it's confusing, because it's gonna it's not necessarily gonna be difficult, but it's gonna be weird, and I'm gonna try and sort of set out a way for you to sort of work through this, like, physically. So hear me out with all this. So what are we going to be able to do today? Today we're going to be able to approximate the area under a curve using rectangles. Um, how we're going to do this? We're going to draw the picture of the curve. We're going to find the areas of the rectangles, and then we're going to add them together. Um, much like how before, in the very beginning, when we were having to do derivatives with limits, and we were having to do, all this complicated stuff because we didn't have anything better. We're sort of about to build something better to stand on for next week. So today we're going to do the approximation, just like, when you were doing slope way back when. And then on Thursday, we're going to be able to do sort of the approximation of what this is, using the limit to take it to what it needs to be. And then starting next week, we'll realize, hey, this is all stuff that we know how to do, and yada, yada, yada. All right, so how do you find the area of a curved figure? Let's say, I don't know, let me just sort of draw a thing. Maybe. It's going to let me. There we go. So we can just sort of draw a thing, right? Let's say we've got this, and I want to find the area underneath this curve. Well, what is, here's my curve, here's my axis. And what I want to find is, I want to find this area underneath, right? Let me make that bigger. I want to find this area underneath this curve. I mean, if we've got a shape that we know, like if it turns out to be a triangle or rectangle or a trapezoid or something like that, then yeah, we can just do it that way. Don't be afraid to break it down into things that you know from geometry. But like here, it's not a shape that we know. So what we're going to be able to do is we're going to be able to sort of approximate this area using rectangles. Maybe this this part kind of sort of on a rectangle. That's not a rectangle. This is a rectangle. I want to sort of say, all right, well, this is about that much. And this one I can move you out the way. Mm. All this being stuck together. Let's unstick it and then move you. There we go. All right. And this one sort of comes up to here, right? I can make a bunch of these rectangles and kind of sort of get an approximation of what this rectangle should be, right? And, there are different ways to approximate it. What I'm doing is I'm sort of saying, all right, well, on the left, we're going to use the left side and make that the height of our rectangle each time, right? And what we're going to try and do is figure out a way to sort of how do we say, just sort of strategize here. We're going to find the area of each of these rectangles. And what's really nice is all these rectangles have the same base length. It's just a matter of calculating the height, which is your f of x. So, and we'll get into a lot more of what this means. But basically, we're going to take all these rectangles, we're going to add them up. Hopefully, in pre-calc or maybe Algebra 2 honors, one of those, you've at some point talked about a sum. But basically, our bases are all the same. It's just this change in x that's happening. And the height is the y value at a certain time. This is sort of like, if we're going to use like really good mathematical definitions, this is what we're doing looks like. And we're going to come back to this later, much later, Thursday, when we get into taking the limits of this, and we're going to find out that this actually turns into an integral, which is nice. But what we want to be able to do is we want to be able to actually calculate these rectangles. And so today we're going to focus on doing this like as if we're still in freshman, sophomore year. We're taking geometry and we're asked to just take a bunch of rectangles and add them up. So once you get beyond the instructions and the idea that what we're doing is like feels like it's going to be more complicated, it's really simple. It's just doing base times height a bunch of times and then adding them up. So don't freak out. So look at what we're going to do. We're going to find out the area under the graph here, and we're going to find the area above the graph here. So we're talking, lower sum and upper sum. We're going to talk about what that means. What I have on the left side here, this is a lower sum, right? Each one of these rectangles starts below the curve. If I wanted to do an upper sum, I'd come from the other side. I'd say instead, all right, well, I'm going to have the y value be keyed off of the end here instead. What we're going to find out when we do this is that sort of the lower sum and the upper sum kind of split the difference between the area. Like if I were to take the lower sum and I were to take the upper sum and I would average it, that average would be significantly closer to my area than any of these would be. But we're starting with rectangles. Let's start with rectangles. Let's work on rectangles here real quick. So again, take a second before you do anything else. Think about what we're dealing with. We're dealing with y equals 7x squared, and we only care about this curve going from x equals 0 to x equals 4. So if we sort of get a little picture here, at 0, we know that the y value is 0, right? 7 times 0 squared. At 4, we get 7 times 16. What is 112? 32. Yeah, 112. 7 times 1 is 7, plus 4 is 11. Okay, so we sort of get a picture that looks like this, right? This is what we care about, and we want to get the area of this graph. So look at what we're working with. We've got this area right here, and let me shade it in. This area in here is what we're trying to figure out. And what we're going to do is we're going to approximate this with rectangles. We're going to say, all right, well, let's pretend like we've got some rectangles that we can sort of put in there. So they either want it approximated with 2 rectangles or 4 rectangles above or below. Let's start with 2 rectangles. Let's see, it's about halfway. It's not too bad. I'm doing okay. It's not too bad. All right, so here's the plan. What we want to do is we want to approximate this with rectangles, right? So the y value, and since we're doing the lower sum, we want underneath, right? So the y value here underneath for this one, and the y value here underneath this one, these 2 rectangles are going to represent our sum, right? So what we can do is sort of figure out what's our base and then what's our height for each of these triangles. Well, let's think about it. Here, the x value is 0, right? Well, what's the y value? 7 times 0 squared is just 0, right? Here, the x value is 1, right? 2 equally spaced rectangles going from 0 to 4. That means x is 2, right? Well, what's 2 squared times 7? What's 4 times 7? 28, right? And then here, at the edge, here x equals 4, and 16 times 7 is 112. Right? So these are all the numbers that we need, right? Our base has a length of 2. And for this rectangle, we want the lower stuff. So look, here this rectangle has a base of 2 and a height of 0, right? This one has a base of 2 and a height of 28. So if I do this and I find the area, 2 times 0 is 0, 2 times 28 is 56, and then I add these together, and I get 56. So if I'm working with 2 rectangles of equal width, right, then their area approximately is 56 units. So since we're here with these two rectangles, let's find the upper sum now. Let me get rid of this. Everything else is going to stay the same. I don't want to change anything. Don't reinvent the wheel with this. Don't reinvent the wheel. Get your answers because they're all going to use the same information. Don't try and overthink this. Don't try and overwork this. Now we're coming from the other side, the upper sum with these two rectangles. Well, what's the base and the height now? Well, here the base is still 2. Now the height is this. The y value is 28, right? Here, the base is still 2, but now the height isn't 28 anymore. It's 112, right? So now let's do this together. Now this rectangle has an area of 56. This rectangle has an area of 224. And again, we're going to just add all this together. 0, carry the 1. 2 times 1 and 5 is 8. 280. Right? And the reality is this 56 number is a little too small. This 280 number is a little too big. If we were to average them, we'd come up with something a little bit closer. And you're gonna see what I'm talking about as you go through some of these problems. So that's with 2. Now what I want to do is I want to do the exact same problem. But now instead of having 2 rectangles, I'm going to have 4. And I'll tell you in advance, what we are expecting is with 4 rectangles, the approximations should be a little bit closer to the middle. All right, so let me erase all this. And I'm not gonna lose any of this information that I already have, because I already have a bunch of information that is already super good. Let me delete all these because I don't want those though. I want to have all these have the same width. So look, now with 4 rectangles, wrong thing here. With 4 rectangles, look what's going to happen. So let's start with the lower sum again this time. There's 1 rectangle, and I'm going from the bottom. Let's see if I can make that a little bit smaller. Coming from the bottom of the curve. That one fits very nicely. And then here's the last one. Coming from the bottom of the curve. So here's the deal. Now we've got 4 rectangles to work with. So let's get more information into our picture. Well, if this is at 0 and this is at 2, this had better be 1, right? And if I plug in 1, my y value is going to be 7. And if this is 3, 7 times 9, right, is 63. There we go. So nice and neat for everything. So, and if you wanted to, you could actually make yourself a little chart down here if it's easier. I've seen people do that. They'll go through and they'll sort of make a nice big XY chart. They'll have the X's on the bottom and the Y's on top. And that's up to you. I'm not going to tell you what to do and what not to do. But however you want to put your information in there so that you understand what's going on. Now for this lower sum, okay, so the y value is the value out here on the left. So this rectangle right here has a base of, now it's not 2 anymore, right? Now we have a base of 1. And what's our height? Here our height is 0. Our second rectangle, again, has a base of 1. Now what's the height? goes up to 7. Our third rectangle, our third rectangle, again, a base of 1. What's the height? It's going to be 28. Again, because I want to pick the vertex that's on the lower side because they say lower sum. And then this last one, the height's going to be 63. And so we're going to go through and we can add all this up and we get 98, right? 1 times 0 is 0. 1 times 7 is 7. 1 times 28 is 28. 1 times 63 is 63. And so we end up with, what did I say, 98, right? Which is a little bit closer to the middle. Now let's see what happens when we do the upper sum. All right. So again, don't reinvent the wheel. Keep this information that we have. Keep this information that we have so that we can do these problems and have them be easy. If you're spending all of your time trying to do the exact same problem from whole cloth like 50 times, you're going to kill yourself. Don't do it. It is not worth it. Save yourself the aggravation. Save yourself the stress. So now, once again, let's make our areas of our rectangles. Again, our width is 1. Our height, now we're on the right side, so it's 7, right? Our width here is 1. What's the height of our second one? It's 28. Here, again, our width is 1. What's our height? 63. No, 1 times 63. And the same thing here, our area is going to be 1 times 112. Well, if we do that, look what we got. We got, let me do some mental math here. We got 70 here. We've got 140, 210 total, right? 70, 140 is 210. And again, you notice this upper sum, smaller than the upper sum with just 2 rectangles. It's closer to the actual answer, just like this one is closer to the actual answer. In reality, in reality, it's going to be something like 120 something, I bet. We'll talk about how I was able to sort of do that in my head later. But for now, basically that's the idea. You're just making rectangles. Don't try and do too much. Don't try and be extra with this. Just make rectangles. Use the rectangles whose height is given by the value of the function at the midpoint of the rectangle's base. So now, remember when I was saying, like, it would be better if we could sort of do it halfway in between? Well, here's halfway in between, right? So look at what we're going to do. Our function is x cubed, and we're going between 2 and 4. And again, you know what x cubed should look like. This, and we're going from like 2 to 4. So we sort of are looking for this piece right here. And we want to figure out what this area is underneath this curve. So first we want 2 rectangles. Well, if we want 2 rectangles, what's halfway between 2 and 4? 3, right? So once again, here's our x values. Let's find our y values. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. So once again, we want to estimate the area underneath the graph using the midpoint. Well, what's the midpoint of the rectangle? What's halfway between 2 and 3? Isn't that 2.5? What's 2.5 cubed? That's a good question. Let's find out together. I don't want to have to do that. So 2.5 to the third is that, 15.625. What's halfway between 3 and 4? Well, what's 3.5 cubed? Good question. $42.875. Great. So here's the thing. We want the height to be the middle height. So this is what we want. So here we know that our base is 1. Our height is going to be this 15.625 number. Here again, our base is 1. Our height is this 42.875 number. Well, 15.625 plus, these are the areas of the two rectangles, gives us 58.5, right? So the area here, using the two rectangles, we've got 58.5, and that's if we estimate it with the two rectangles. What about if we want to use 4 rectangles? Well, hold on. That just means we have to cut this in half again. So we've already done all that work, which is great, right? We already have our 4 rectangles here, 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 and here. So we know each of them, the width is 0.5. Now we need to find the height. Well, it's just what's halfway in between, right? Well, what's halfway between 2 and 2.5? 2.25. Well, what's the y value for that? That number, right? So already, three, 0, 6. I mean, it doesn't matter what the numbers are. Base times height. Calculators are totally fine for this, as far as I'm concerned. And you're going to do the exact same thing, right? You're going to say, all right, well, what's halfway between 2.5 and 3? 2.75. Well, what's the y value for that? Because we know that our base is 0.5. What's our y value when we plug that in to 2.75 raised to the third power? 20.796875. And and again and again and again, right? This is going to be 3.25. We're going to throw that into the calculator, see what that is squared. 3.25 cubed. 34.328125. 34.328125 times a half. And then, again, 3.75 here. And then we're going to do the exact same thing. 3.75 raised to the third power gives us 52.734375. And then just times a half. So, I'm just going to divide by 2, right? 10 divided by 2 is 5, carry the 1. 6, carry the 1. 4, carry the 1. 3, 1, 2, 5. Do the same thing here. 6. It's 4. 3, 7, 5. Divide this by 2. 17.1640625. This one 26.3671875. And then just add them all together, whatever this is. 5.6953125 plus 10.3984375 plus 17.1640625 plus 26.3671875 is that number. So these 4 add up to 59.62503. Hey. And again, if you've got a calculator next to you for a problem like this, especially for a problem like this one where it's like decimals and stuff, it's a 2-minute problem. It's just tickety typing on the calculator. All right. But it's the same idea as what we were just doing here. It's just now instead of having the one of the endpoints, it's the middle point. So let's look at another problem. This is more of a, shall we say, application type thing, but it's the same idea. They're telling us, here's the velocity. We want to know how far we went. So like, okay, so are we, right, at every 10 seconds, right, we get a certain amount of distance, right? 10 seconds, we went 26 miles an hour. Another 10 seconds, we were going 41 miles an hour. So the time, it's every 10 seconds, and then we check the velocity, and we use that for the most recent 10 seconds, is basically what we're saying, right? So basically 10 times this plus 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 10 times this plus, and just going all the way through, right? And that's all you're doing. So what's really great is that you don't have to do 10 times this plus 10 times this plus 10 times this. You could instead do 10 times all these added together in it. Because think about it like this. We've got 10 times all of these, and we're adding those together. So let's just factor out the 10. Add these all together. And then just add those up and multiply it by 10. You know, right? Don't do too much with this. I'm still going to do too much. 7, 15, 24, 2, 3, 7, 10, 12, 14, 15. Then I'll add all these up. I don't care about this one, right? One, 2, 11, 12, 18. Carry the 1, 2, 6, 8, 12, 16, 19, 20. We can just add these together. So all we're going to do is 10 times 362, right? Which is just whenever you multiply by 10, just put a 0 on the end. And so now be careful. An answer like this is going to want a unit, right? Well, what's our unit? How long is the road? What units have we been using this whole time? Feet and seconds. Well, length is a one-dimensional unit of distance, so feet, right? Because look at what we did. We did seconds. That's a number 8. I want the letter S. Seconds times feet per second. So they're going to cancel out those seconds, right? And so our final answer is just going to be right there. Let's do the next one. All right, an object is shot straight upwards from sea level with an initial velocity of 700 feet per second. Assuming that gravity is the only force acting on the object, give an upper estimate for its velocity after 5 seconds have elapsed. What is the biggest that could possibly be? All right, so an upper estimate. So what we're going to say is we're going to use the bigger numbers. But let's what are our numbers? Where do they even come in? Well, let's think about it. At time 0, our speed is 700 feet per second, right? Well, what about at time 1? Well, time 1, we know that the acceleration due to gravity is 32 feet per second downward, and we're shooting upward. So we're going down 32 feet per second every second. So if we're going down 32 feet per second every second, aren't we at like 668? Well, what about at 2 seconds? Well, we're going down another 32 feet per second. What about at 3 seconds? Well, we're going down another 32 feet per second. Well, what about at second 4? It's the same thing. Right? We're just going down 32 each time. Right? 1, 2, 3, 4, 5 seconds have elapsed. So what we're going to do is we're going to use our this right here, right? So after 5 seconds have elapsed, we should be expecting, it's not going to be perfect necessarily, but we should be expecting our answer could be that, right? Upper estimate. I bet you they want this 572 because it's coming from, because again, we're thinking about these rectangles, right? And you notice how they're getting smaller? So they probably want this height, which is the 572. So if it were me, I would put my answer 572 feet per second. After 5 seconds, then it would be like 540. But we're here. All right. So part B, now we're going to figure out how high it got. Well, if it was going 700 feet per second for a second, we're using the lower estimate now. So we don't care that it started at 700. We're going to say, all right, well, look. After 1 second, it's gone 668. And then after another second, it's gone 636 feet in 1 second, right? And then 604, 572, and 540. Since they want a lower estimate, so we're just going to add all these up together. And this will tell you how high it got. All right, let's see. So this is 10, 10, 20. 6 and 4 is 10. 3 and 7 is 10, 22. 6. So 5 and 5 is 10, 15, 21, 16, 22, 28, 29, 30. Yeah? Yeah. So how high did it get at after 5 seconds? The lower estimate would be 3020. Again, don't think too hard about these. Here's your last one. So what we're going to do, and I'm not going to be able to do this well, but we're going to try. Make a big old circle here. And what I want to do is I want to try and inscribe a square. Let's see if I can make that picture work. Kinda. I want to do better. I was closer. All right, pretty close. I want the square so that all 4 corners touch the circle. That's what I want. There we go. That's pretty good. So first things first, we're gonna want to know what's going on here. The circle has radius 1. Let me put a little center of the circle there. And we're gonna do a radius. It's gonna get mad at me because I'm using the same color for everything. Let's make you blue. There we go. So the circle has radius 1, right? Well, if the circle has radius 1, what we can do is make a bunch of radii. This is radius 1 as well, right? Radius 1, radius 1. So here's what I'm doing. We know how to find the area of a triangle if we have the two sides and the angle in between, because that's 90 degrees, right? For a square. 1/2 AB sine theta. We know sine of 90 is 1, so we don't have to do that. So 1/2, 1 times 1. Right? So this triangle right here is 1/2, and there's 4 of them. So we can multiply that by 4. And so what we get is, if this whole thing is 1/2, then the square has a area of 2. Another way to think about it, if you're one of those 30, 60, 90, 45, 45, 90 triangle people, this is a 45, 45, 90 triangle. In order to get from the leg to the hypotenuse, that has a length of radical 2, right? Times radical 2 to get from the leg to the hypotenuse. Well, area of a square is side squared, so radical 2 squared is 2. Either way, you get the answer of 2. So now they want an octagon. Well, hold on, that's 8 sides. Can I do this? Probably not. I'm gonna leave the square here. Then I'm gonna try and be sneaky. And draw a line like this to make an octagon. Am I gonna be able to do it? Oh, it's snapping to where I want it to snap. That's good. That's great. That's exactly what I wanted. Hooray. This is pretty close to being. I ain't getting the one with the 16 sides. That ain't happening. So, but look, so here we have an octagon, right? And what we want to do now is the exact same thing. Well, wait a minute. Hold on. Let me take this guy. Now we can do the exact same thing. I just basically cut the angle in half. Each of these are still 1, but now this is a 45-degree angle. And now instead of there only being 4 of these, there's 8 of these, right? Times 1 times the sine of 45. And we know 45, or pi over 4 if you prefer. Sine of that is radical 2 over 2, yeah? So we got 8 times a half times 1 times 1. So we got 4 times radical 2 over 2. Or if you prefer, 2 radical 2. After this one, it ain't gonna happen. We know that the half of it just gonna cut the angle in half again and multiply the number of triangles by 2. So now instead we're doing 16 triangles times 0.5 times 1 times 1 times the sine. And I am in radians, so I'm going to put pi over 8. Pi, where's the pi button on here? There we go. Second pi over 8. And we get 3.0614 something something. Six, 7, 4, 5, 9. So here's the thing. why are we doing this? Well, first of all, we're inscribing these to the circle, and we know that the circle, pi r squared, well, the radius is 1. The circle area is going to just be pi. 3.141596, etc. 2 times the square root of 2, because, we did do that one earlier. We wrote it out as a radical in simplest form, but this is 2.8 something. So look at what's happening as the number of sides grows. What's happening to the area? I bet if we did more and more and more sides, we'd get closer and closer and closer. Let's do a couple more. If we had 32 sides, again, this is just gonna double the number of triangles again and cut the angle in half, right? So we can think about it like there's n sides times 1/2 times 1 times 1 times the sine of 360 over n, right? That's what we're working with. And I can actually plug that into my grapher so that I don't have to do all this on my own. That is not what I wanted to do. I wanted an x times 0.5. The 1 and 1 go away, times the sine of 360 over x. Close parentheses. So if I do this, I'm going to start to see something really cool happen. Let's see what my window is set at. Let's do my x minimum is 0. Well, let's make it 1. We can't even really have one side, can we? Let's make it 3 sides. That's the minimum number of sides you can have, and let's make the maximum 1,000. And then the y min, well, we can't have an area below 0, so let's make that, and then let's make it like 5 for the y max. So let's see what happens. Let's graph this. That looks so cool. Did I do that right? Well, what happens here? Let's use our trace. So it's gonna be weird because you can't have like decimal number of sides. But look, if we have a square, how did that not give us what we wanted? Oh, you know why? Because I'm in radians. That would be why. This is why it's always important to remember that radians and degrees to pi delete. See, now this is going to look really cool. Let's try this again now. Hey, there we go. That's what I was expecting. All right. So look, what happens when we have 4 sides? Well, just what we said, right? 2, 5 sides, 6 sides, 7 sides, 8 sides. We should get 2.8 something. Hey, that's what we got. 16 sides, 32 sides, 64, We keep going. Look at what is approaching. 3.14151 when x is 500. It's 1,000. When it's 10,000, I'm out of the window, so it won't. It's going to yell at me. Gonna make me quit, and then I'm gonna put like 3 more zeros on the end of here. That's more than 3, but that's okay. But anyway, so $10,000. You know, just as we keep going, we're getting much and much closer, much closer to pi. This is what's happening. I don't know how far it's going to yell at me again. No. But the point is there. It's approaching pi. It's approaching the circle. And this is one of the reasons why in like really high level geometry, sometimes we think about a circle as a polygon with infinitely many sides. Other people might say, hey, it's a polygon with no sides. Both of those work in different contexts. But the point that I'm trying to make here is that this is very akin to what we're about to be doing. When we come back on Thursday, you know, before we were taking these problems and we were breaking them into rectangles. We were taking and, you know, slicing it into 2 pieces and approximating them. Here with the square, we were slicing it into 4 triangles. With the octagon, we're slicing it into 8 triangles. With the 16-sided, we're 16 triangles, and so on and so on and so on and so on and so on. And eventually, as we get more and more and more triangles, we approximate the circle better and better and better. And what we come up with is a sum for this circle, a sum that not only approximate this circle, but as we go to infinity, we actually make the circle.